Hi everyone, welcome back to the chemistry lecture series. Today we're going to be talking more about atoms. Specifically, we'll be referring to some notation, some more mathematical means of treating elements. We're going to talk about elemental symbols. We're going to revisit our subatomic particles. We're going to give numbers to them and notations. Then we're going to talk about isotopes, and then we're also going to talk about isotopic abundance equating to the average mass of an atom. If you picked one out, what would be the mass on average, even though they're quantized particles? Anywho, let's get into it. So I want to begin by reinstating the subatomic particles that we talked about from the last lecture. So if you remember this, so be it. If not, well, that's life. We will remember it right now. So remember that a proton, there's a proton, there's a neutron, and there's an electron. And if we consider the mass, well, a proton has a mass of 1 AMU. A neutron has a mass of 1 AMU, and an electron has a mass of 0.005 AMU. Okay, so remember that the electron is only a fraction of the mass of the proton and the neutron, but when we consider charge, remember a proton has a charge of +1, a neutron has a charge of 0, and an electron has a charge of -1. So keep that in mind. That's going to be important in our future talks here. So let's talk about symbols. So when you have an element on the periodic table, it's common to refer to a symbol for them. So every element, remember, an element is a distinct proton count. So if you have some number of protons, you have a specific element. Now, if you have something like hydrogen, you have 1 proton, and we denote that with a big H. So these symbols here are going to denote which element we're talking about. And we're going to put the proton count right here. So if you have a proton, you have a proton count of 1. Okay, but let's say, for example, you have iron. Okay, iron is another way to write a symbol. And we write Fe. It comes from the idea of ferrous. That was I believe that's Latin for iron. But you also have other symbols, like, for example, gold is Au. So just know that there's this notation out here. We won't be so worried about the numbers for the other ones, but you have hydrogen, iron, gold. Get familiar with these symbols. You'll find them on the periodic table, of which we'll talk about in a later episode. But yeah, just keep this in mind. Symbols, what element are we talking about? And you've probably seen this before in maybe past chemistry courses. Okay, so let's talk about the atomic number and the mass number. So Z in our case is going to denote the atomic number. And it should be stated that the atomic number is the proton count. Okay, so the proton count is the atomic number, and we denote that Z. We also have another number, A, and A is the mass number. And remember, when we talk about a nucleus, we might want to know how many particles are in the nucleus. Remember that in the nucleus, there's protons, right? So the proton count here is 2. That would be Z. But A is the mass number. It refers, and when we talk about a mass number, we're including these things that we call neutrons. All right, so the mass number is protons plus neutron count. So notice the difference. Please, this is very important. Your proton count is your Z number, which is these little dark shaded circles here, but the mass number is everything. It's the protons and the neutrons. So in this example, this is a helium atom, In fact, I'll draw it a little more accurate. We'd have 2 electrons, but in the nucleus of this helium atom, we have 2 protons, 2 neutrons, so Z is equal to 2, but A is equal to 4. Okay, so that's important that you understand these 2 different things. And if you want a more sophisticated approach, well, Z is the number of protons, where A is the number of nucleons. Well, what about N? Okay, let's define N to be the number of neutrons. Well, if A is the total number of nucleons, both protons and neutrons, and Z is the number of protons, well, we find N by just taking the difference between the 2, right? Because 4 includes protons and neutrons, Z is just protons. You subtract out the number of protons, you get the number of neutrons. So in a helium atom, we have 2 neutrons. Okay, let's get a little more symbolic with what we're talking about. The best way to denote atoms, so this would be a helium atom, like I said. General notation will follow this. Now, if I could find an eraser, be right back. All right, so sorry about that. Notation will follow like this, and you'll see this all throughout chemistry. If we have some element X, X is a made-up thing. It could be iron, it could be gold, it could be hydrogen, it could be carbon, nitrogen, oxygen, phosphorus, whatever. The way that we denote this is we have a charge, plus or minus whatever the magnitude of that charge is, and we're also going to have some number Z up here, which is, wrong way. A goes here, the mass number will go up here, but the atomic number will go right here. So I can give you some examples and we'll work with these. If I have neon 20 and I have a proton count of 10, well, tell me some things about this. Okay, first I want to know, is it charged? Okay, is there a charge on that atom? How many protons and how many neutrons? Okay, so see if you can answer these and we'll reconvene. You can pause the video or else I'll just keep going. Okay, so hopefully you had a second to maybe do those problems, just answer the questions. So let's go through them. Is neon charged? Well, for there to be a charge, there would have to be a number here. Now, if there's nothing there, it's a charge of 0. There's no charge on it. There's no deficiency or greatness of electrons here. All right. If we have this number up here, this is the mass number, right? So this is our A. So A equals 20. So there's 20 nucleons here. There's some amount of protons, some amount of neutrons. Okay, if we look at this 10 down here, we know that this is the atomic number, which is the proton count. So we know that there's 10 protons. So how many protons? Well, there's 10. Okay, is it charged? No. But how many neutrons? How do we find that? Well, we just did it over here. Recall that number A, the mass number, is 20 nucleons, but Z is only 10 protons. So 20 minus 10, that leaves, if we have 10 protons, that must mean we have 10 neutrons. So there's 10 neutrons here. What if I did this? What if I raised this count? And what if I did so that it's now 21? What changes? Is it charged still? No, it's not charged, right? Because that number didn't change. How many protons? You still have 10, right? I didn't change the number of protons. That must mean that I added a neutron. So this is not 10 anymore. This is 11. All right, so get comfortable with working with this stuff. Let's do one more just to get it down. After this, we'll talk about one more thing about charge. I'm just going to write that down that I talk about that. Okay, let's talk about uranium-238, which has a number of 92 down there. Okay. And let's say it's +1. Okay? So go ahead and answer the questions again. Is it charged? How many protons? How many neutrons? Okay, so is it charged? Well, notice there's a +1 here. We'll talk a little more about what plus and minus mean for charge. But for +1, yeah, there's a charge there, so yes. Okay, what about what about the proton count? How many protons are there? Well, this number down here, Z, is the atomic number, and it tells me the number of protons, which is 92. Okay, but how many neutrons? Remember, it's going to be the mass number minus the atomic mass, which if I grab a calculator, I'm going to do 238 minus 92, and I'm going to find that the number of neutrons is 146. All right, so please get familiar with that. It's going to be a big thing on any exam you'll take, finding the number of neutrons, protons, and if it's charged, stuff like that. Okay, I'm going to go ahead and erase this. Let's talk a little bit more about charge. So notice here that I denoted that these atoms can be plus or minusly charged. Okay, what does that actually mean? Okay, if I have some element X and it has a +1 charge, well, we refer to that, or just a positive N charge. So N being any number, any real number. Typically, you don't see past 3. Maybe you'll see +8 or something, rarely, but plus N, just any number. This is what we call a cation. All right, so if you have a +N charge, you're a cation, and you specifically lost an electron. Okay, but if I have X to the -N, so in the magnitude is switched, well, this is an anion, and he gained an electron. Or 2, or 3, or 4, however much N is. Let's go through an example just to see the difference, because I feel like that is the most fundamental thing to understand, is what actually does charge mean? Like, what is the positive and negative referring to? Well, here's the best way I can describe it to you. If I have a hydrogen atom and I lose an electron, so out comes an electron, it gets shot out of the molecule, we're going to have H+, which is just a proton. So let's visualize that. All right, so if I have a hydrogen atom, hydrogen has 1 proton and 1 electron. So let's draw that. Okay, so in the normal state, we have a little itty bitty electron here, and we have a proton. Okay, but once this is called an ionization event, because we're going to form something called an ion. These guys, they're called ions. All right, ions are just particles that have charge, right? During an ionization event where you form an ion, well, you keep the proton there, but what happens is now the electron gets shot off the molecule into space somewhere. So let's say just gets shot off like that. Well, let's think about the charges that are happening here. So let's consider that. If we have a proton, well, we know a proton is a +1 charge and an electron is a -1 charge. So if we look at hydrogen overall, +1 minus 1 equals 0. But in this, the electron is no longer associated with the atom. So all that's left is a +1 charge from the proton. And that's where we get the +1 charge from. I hope that sinks in for you, because it's very important that you understand this charge notation, because some people, they just really struggle with the idea of charge. And that was a struggle point for me in high school, at least. So I hope that this visual helps you. We're just going to go through it one more time to make sure that you really got it. Here is our notation. A is some mass number that refers to the total number of nucleons. Z is the proton count, and this thing that we call charge. Remember, charge is just an ability to basically be manipulated in an electric field or a magnetic field. Think about it like that. Susceptibility to a field. It comes from this idea that atoms can lose electrons or gain electrons, right? So it's an excess of protons or electrons. And we can denote them with a positive N number, which is a cation, which means you lost an electron, whereas a negative N is an anion, and you're going to gain an electron, ions. If you have trouble remembering the names of cation and anion, remember that cations are positive. Little cat here for you. I'm not the best artist, so bear with me. But positive charge cation, you lost an electron, right? That's what we demonstrated here. However, an anion, negative N charge, you gain an electron. I'm going to show you just one more because I think it's very important that you see it. Let's do an anion event, so gaining an electron. We call it an electron affinity event. So let's say we have some nucleus like this. All right, so maybe add a little more. So this is a lithium atom. Lithium doesn't like to gain electrons, but let's just say he does. And you don't need to know why that is right now, but you know. So typically he'll have 3 electrons. So this is lithium 6, 3, right? Looks like that. But let's say a nice little electron comes in and wants to join the party. In fact, when we learn orbitals and electron configuration, there's enough space. Now, this isn't really how it looks. There's 1s, 2s, we'll get to that. This electron, I'm just saying that in case any of you like math whiz, chemistry whizzes are like, that's wrong, off with your head. No, I'm just trying to keep it simple, guys, as much as I can. Chemistry's a weird subject. Anywho, back on track. You have this electron right here, and he's going to begin to want to come into this atom. So let's say he does. And I'll ask you one more question. Before the electron attached, is it charged? Well, you'd say no, because the electron, -1, -1, -1, right? The protons in the middle, +1, +1, +1. There's an overall charge of 0 here. Okay, but once we add that electron, what's going to happen now? Well, notice now there's 4 electrons. So let's count the total charge. 4 electrons, which each have -1, so -4. We have 4 protons, which contribute, or sorry, we only have 3 protons, G's. 1, 2, 3. And that's going to give us an overall charge of -1. So this is lithium, same number of nucleons, same number of protons, but in this case it's a -1 charge. So very fundamentally important stuff that we need to talk about, and that's it there. Okay, so hopefully you understand cations and anions. We're going to talk about one more thing, and that's what happened. Basically what we're going to talk about is what happens when we add another neutron to the mix, okay, to a nucleus. Let's first just fundamentally know what an isotope is. So an isotope is the same proton count however, same proton count, however, different mass number due to differing number of neutrons. So I'll show you the most easy to visualize example of this. And that's going to come down to this beautiful thing called hydrogen. Right? Hydrogen, we know has a mass number of 1 because it has 1 proton and a proton count of 1. And it looks something like this. All right, but what about this other element I could draw? Maybe I could raise the mass number to 2. So this is hydrogen. But we actually give this guy a special name. What he looks like is he has a proton, but then he adds a neutron, okay? And the electron count stays the same. Notice that the charge didn't change, right? Because I have 1 proton, 1 electron, 0. 1 proton, 1 electron, 0 overall charge. So all we did was we added a neutron and the mass number raised to 1. But notice the proton count did not change. We call this deuterium. You've maybe heard of a deuterium lamp before, if you've ever worked with one. I don't see why you would, but let's say you did. So an isotope, remember, proton count is the same, but the mass number is different because we added a neutron. Let's talk about the most fundamental idea of isotopes, and that's the idea you've probably heard of C13 versus C12. What does this mean? Okay, well, carbon has 6 protons, and that's not going to change. If you are a carbon atom, you have 6 protons. The Z number is defined as the element you are. If you have 1 proton, you're hydrogen. If you have 2, you're helium. If you have 3, you're lithium. If you have 4, you're beryllium. It defines who you are. Protons is your identity. So keep that in mind. Anywho, carbon, if we have carbon 13 versus carbon 12, well, let's think about the proton count, the neutron count, and we'll go from there. Well, the proton count is the same. It's 6 and 6, right? Because that's what the proton number is, or the atomic number right here. But what's the neutron count? Well, 13 minus 6, what is that? Geez. 7. We have 7 neutrons in a C13 atom, but in a C12 atom, it's 6 minus 12, and that's only 6. So notice the difference. All we did is we added another neutron to C13, okay? So keep that in mind. These are isotopes. There is an important distinction, though, and that's the fact that there are different abundances. So let's talk about the percent abundance. So what's the percent abundance of these in nature? Well, it turns out that C12 is the most abundant at 98.99%. And C13 is only abundant at 0.01%. All right? So if we took a bag of a billion gazillion atoms of carbon and we looked at every single one individually, only 1% of them on average would be a carbon 13 atom, whereas the majority is going to be carbon 12. And there's no reason that you need to understand, at least at this point, for why that is. Sometimes it's radioactive stability. There's probably some weird physicsy thing happening there that I just don't understand. Okay, now let's do just one more example of isotopes, then we'll talk about using these percent abundances to find an average mass, which is really helpful in analytical calculations in a real-world application. Let's talk about lithium again. Lithium with a mass number of 6 versus a mass number of 7. Okay, proton count, neutron count, percent abundance. Go ahead, see if you can do that. If you got it, you're good to go. Well, we have 3 protons in each, but the neutron count's different. Here in lithium 6, we have 3 neutrons, right? Because 3 of those nucleons are are protons. That leaves 3 to be neutrons. But notice here that's 7. Now it's 4 neutrons. I guess you wouldn't know the percent abundance, and I didn't write it down. So that was a really stupid question. So if you searched it up, brownie points to you, right? Some amount. Smiley faces is okay. All right, let's talk about this idea of average mass. When we're in the real world and we want to make calculations, and we'll see this later, it's not going to be very important. What I'm going to say is not going to be very important to you. But let's say I don't know, cut the tip of this eraser off, or marker off, okay? And I put it on a scale. It's going to have some number of, say, carbon atoms, like we discussed over there, okay? It's going to have 98.99% of those carbon atoms will be carbon-13, and they're going to weigh some amount on a scale. But the carbon-13 that we have is only at 1% abundance, and we have to equate for that because that slight mass imbalance can actually throw us off quite a bit. This is best seen when you work with bromine. If we went with the bromine mass number of the isotope 79 versus 81, for example, well, the 79 mass is 2 nucleons less than the 81. And that's going to, and what it turns out that they're equally as abundant to each other. So they're 50-50. So what we do is, in the analytical sense, is we go right in the middle. Instead of 81, 79, we go in the middle at 80. So let me just demonstrate that quick. We have bromine 79. We have bromine 81. Okay, they're about 50% abundant in nature. So if we have, let's say on a little weighing scale, we have bromine. Okay, that would be really weird because it's a gas, but let's say you have liquid bromine in an ampule or something. You put it on a scale, and which mass do you go with in your calculations? Do you go with assuming it has all 81 or all 79? Well, you can't really do that. You have to go in the middle, and it turns out we go with bromine 80. But how do we just mathematically treat this? It's gonna look something like this. Okay, so the average mass can be found, and if you never had calculus before, this is okay. It's really not, it's algebra, basically. I'm gonna use big notation. The sum of, so this guy right here, that big sigma, that just means the sum of. So add up a bunch of these things together. That's what that's saying. The fractional abundance times isotope mass. And if we wanted to draw out this sum, it would look something like this. So we would have percent of fractional percent, so decimal points, fractional percent of isotope 1 times mass 1, and then we'd add that and we'd keep going until we got to the last mass. So percent isotope for n, so n being the nth one or the last one times the mass of n. If you're confused, that's okay, because I was when I first learned this. Let's do an example so we can understand it. We'll start with carbon. We'll do another one with boron. And then that's the lecture, guys. That's all we're doing today. So let's consider C13 and C12. At these abundances, what is the average mass? Well, I'm going to be more leaning on the 12 side, and in fact, we'll find that that's true. But let's do that. Percent abundance in fractional form, if you recall, looks something like this. 98 point... one second. Hydration is important. Fractionally, this is 0.9899, where this is 0.0101, right? So just remember that if you want to convert a percentage into a fraction, divide by 100, okay? Keep that in mind. Fractional forms of percentages, you just divide by 100. Okay, now let's go ahead and find the actual mass of these. So we're going to follow this formula, the sum of the fractional abundance of one isotope times the mass of that isotope, and you keep going. Work in AMUs here. You can work in AMUs, you can work in kilograms, whatever you want, but just don't work in kilograms, okay? Because you're going to have to convert to AMUs. If I say, oh, the mass of one atom is 2.4 times 10 to the negative 30 kilograms, well, you're going to just look at me like I'm damn crazy, okay? So don't do it. Work in AMUs, all right? Okay, C13, we're going to start our calculation as such. So the fractional abundance, we're going to start with C13, is 0.0101. And the mass of one of the C13 isotopes is about 13 AMUs. It's not quite 13 AMUs, but it's close enough for our calculations. I have an example where we get a little more specific with the mass in that regard, but this is just to show you what we're doing. So the fractional abundance at 0.0101 times 13 AMUs plus, and now we're going to talk about this one. So this is our first term in the sum. This is called a summation. It's the first term, fractional abundance, isotope mass, fractional abundance, isotope mass. Then we're going to take the fractional abundance of the C12, which is 0.9899, and multiply it by 12, right? Because this isotope weighs only 12 nucleons, where this one is 13. And when you calculate the summation, what we're going to get in our summation is a mass that takes into account both isotopes and outputs with the fractional compositions of each in nature a mass that is more reflective of what you would find in the real world. So let's go ahead and calculate this, shall we? So this is how you want to type in your terms, right? So this plus that, all right? And when we calculate it, it turns out that the average percent mass of a carbon atom is 12.01 AMUs. All right, so the average percent mass, 12.01 AMUs. Hopefully you found that really cool. Notice that, let's actually take one more interpretation of this, just for the shits and giggles. The average mass, I should say, not average percent, but the average mass being 10.01, notice that it's practically carbon-12. So in nature, we treat carbon as carbon-12. We don't really consider C13 because it's so non-abundant. And on average, the mass is more reflective of the C12 isotope than the C13, but notice it's there. And in fact, there's applications to that. There's radiometric dating for the C13 to the C12. It's now, people have the misunderstanding that we date fossils that are past 7,000 years old with C13. In fact, we really don't because it's not the best way to date something, but there's other radiometric dating labels, right? There's other things that we can look at. So if you ever hear pseudoscience, which pisses me off, frankly, don't listen to them because they're liars. All right, let's consider another example, and then we'll call it. Let's talk about boron. Here's boron, the first isotope. One second, I have to see here. I had to consult my periodic table. So boron, which has a proton count of 5, and is a mass of a nucleon mass of 10 AMUs, is found at 19.9%. However, there's another isotope which lays at about 80.11%. Assume that the masses are more accurate than what I had listed, in that such that B10 is 10.0129 AMUs. So look at the precision on that. Right here. Look at the precision. 10, the nucleons, need more water here, sorry. But then we have this little fractional thing, which is helpful because it's equating for the small mass difference between protons and neutrons. Would love to explain that to you, but you need to get some more chemistry under your belt before you can understand why neutron and protons have a mass difference. Very small mass difference. B11 is 11.0093 AMU. So go ahead, use these mass numbers and these percent abundances and find the average mass of a random boron atom you would find in nature. Go ahead, do it. All right, here's the solution. Average mass. This boron 10, it's at, geez Louise, I'm dying here, guys. There's something in my throat that's killing me. And I have no idea what it is. Anywho, so B10 at 19 is 0.199, right, in fractional form, that percent, times 10.0129 AMUs, that's our first term. I'm going to add it to 0.8011, but that's going to be times the 11.0093 AMUs. All right, so the average mass then is whatever this calculates out to be, so let's go ahead and find it. 0.199 times 10.0129 plus 0.8011 times 11.0093. So I'll just show you the calculation quick if you need to confirm with yourself. So bring you back to my first term. All right, so that's the whole calculation, and when we calculate it, we're going to find 10.8. So look at the mass of the boron now. Remember, in carbon, it was really, really close to 12 because 12 was the most abundant isotope. Well, here, similar, right at 80%, the boron 11 is about 10.81 AMUs, right, closer to the boron 11 than the boron 10. However, notice it's kind of more pushing. You see more character of the boron 10 in there, right, when we wouldn't really expect to. So in nature, an average boron atom is going to weigh 10.81 AMUs. That's all I have to say for this lecture, guys. If you enjoyed, please drop a like, comment, subscribe. I greatly appreciate it. I hope that you have a wonderful day. Bye-bye.